Hi guys, let's take a look at the first portion of this confidence interval question. We're going to build and interpret the confidence interval. So in a random sample of 95 WHS students, 70 of them indicated that they had an iPhone. So we're interested in using these data to calculate a confidence interval for the true proportion of all WHS students that own an iPhone. So the sample statistic, in other words, our value for p hat is 70 over 95. That rounds to 0.74. So our statistic is that from our sample of 75 students, 74% have an iPhone. So there are a little over 2,000 students at our school, so the independence condition is met in this situation because even if you take 10 times our sample size of 95, that's 950. That's still less than or equal to the size of our population, so we can act as if our 95 observations are independent of one another. So next, let's see if the sample size above is, quote, large enough in the sense that we're getting the number of successes and failures that are large enough in order for us to believe that we're getting a good comparison, in order for us to believe that the distribution of our p-hats is approximately normal. So the number of successes, that would be n times p. So in this case, n is 95, and our sample proportion is 0.74. So if you multiply those together, you get 70.3. Of course, you could have just gone ahead and used the 70. We had 70 people that had iPhones. That's fine. That's certainly greater than or equal to 10, so we're getting at least 10 successes. The number of failures, that's equal to n times the failure probability, 1 minus p. Well, that's 95 times 0.26. That turns out to be 24.7. It would be perfectly fine to say 25. If there are 70 successes, then out of the 95, that leaves us with 25 failures. That's greater than or equal to 10. We're certainly getting enough successes and enough failures for us to believe that we're going to be able to get a valid comparison here, and we can believe that our sample proportions, our p-hats, are approximately normally distributed. So the independence condition is met. This is what we call the normality condition. Some people call it the condition on the sample size. It's certainly large enough to give us enough successes and failures. And very important, we have a random sample. So we can go ahead and calculate our standard deviation and build our confidence interval. So our standard deviation, our best estimate for the truth is our sample proportion of 0.74. So we're going to use that to find our standard deviation, p times 1 minus p, all divided by n. So that's 0.74 times 1 minus 0.74, that's 0.26, divided by 95. And if we round that to 2 decimal places, it's 0.05. That's our standard deviation. So to build a 95% confidence interval from our statistic of 74%, from our statistic of 0.74, we need to add and subtract 1.96 of our standard deviations. So we're going to subtract 1.96 of these standard deviations. And we're going to add 1.96 of these standard deviations in order to get the lower and upper boundary for our confidence interval. This z-score, 1.96, is connected to 95% confidence. So if you simplify this, this turns out to be 0.642, and the upper boundary turns out to be 0.838. So to interpret this confidence interval then on the other side, takes us halfway through. Here's step 5. So we are using z-scores of 1.96. We're going almost 2 standard deviations above and below the mean, and that captures the middle 95% of the sampling distribution. That's why we say we are 95% confident. that the true proportion of, and in this case we're trying to capture the proportion of WHS students that have an iPhone, so I believe that we are 95% confident that the true proportion of WHS students with an iPhone is between 0.642, so 64.2%, and 0.838, so 83.8%. So that is the building and the interpreting of our confidence interval. So in the next video, I'm going to take you through the rest, questions 6 to 10, where we look at making a comparison with this interval, and we also change the level of confidence from 95 to 99%, rebuild the interval, and see if that changes any of our conclusions.